Okay, so last Fourier day. Last Fourier day, and then we'll start on Wednesday. We'll start talking about actual real pulse sequences. We'll start off with real spin echo sequences, how the ones that you might actually run actually work, because they've been highly optimized, and so there's a lot of. You can understand how the basic one works pretty easily, but as you start to really get them really good, that's where some of the complexities come in. So what I want to do today is, so 3 topics, they're related to each other. So I'll go over that replicas argument again, and then talk about ringing, sort of from a Fourier convolution versus multiplication context. I'll put the replicas argument up again just so you don't get confused with the ringing argument. It's all about sinc functions. And then we'll talk about field of view, kind of practically, like on the scanner. How do you change the field of view on the scanner, and what does that actually sort of mean for the kind of data that you're actually collecting in K-space? And it's actually quite it's very simple equations, but we'll just work through some examples, and then finally, I'll talk about aliasing, which is the same thing as replicas, but I'll just draw out an example so you can see how it works in the case of like a time signal, which is relevant for things like heartbeat messing up your fMRI signal. So, okay, so we'll start off just putting up the argument from last time about why you get replicas, what's going on here. So we'll put up, so there's, let's see, I'll divide down the middle here. So we'll have two examples of multiplication and convolution. So we have here's the K-space side, spatial frequency side, and here's the space side. So on the space side, if we look at, and so this is basically an argument like, why do you get replicas? So on the space side, you have something that sort of looks like a rectangle function, which is the brain, because there's black, and then there's a bunch of brain, and then black. So that's kind of like a physicist's brain. It's just a rect function, just a rectangle function. And what is that Fourier transform to? So this is x, and then this is k. So that Fourier transform to something that looks more or less like a sinc. And so if you've done any of the homework so far, what do you get? You get something that it's got a big bright spot in the middle, and then it kind of drops off very quickly. That's approximately what the Fourier transform of a brain looks like. Kind of looks more or less like a sinc function. So that's this is ft going back and forth. And then what are we doing when we collect data? When we collect K-space data, we're sampling the K-space data. We're sort of discretely sampling the K-space data. And how can we represent that? We represent that as in the infinite case. So again, we're sort of making an argument with an infinitely finely sampled Fourier transform. And what we do is we just multiply by a bunch of spikes. So here's a bunch of spikes, and those are our sampling spikes, because we're instantaneously sampling a spatial frequency at each k point, etc. So if we multiply that bed of nails times this function, then we get out of that our sampled k space, and so it looks just like. It looks like the sinc, like that, but it's just discretely sampled sinc. And so there's zeros in between in our infinitely fine representation of that sinc. So there's So basically there's one sample there, another sample there, another sample there, etc. And so the question is, why does that generate replicas? And so our little graphical argument was, well, let's take the inverse Fourier transform of that set of spikes. And what is the inverse Fourier transform of the set of spikes? It's actually spikes. It's just another series of spikes. We could write out the equation for it, but it's relatively intuitive, because if you jam these sampling spikes closer together, it spreads out these spikes. And so imagine if you jammed them infinitely close together, these spikes would spread out infinitely. You'd end up with one spike. And we know that like one spike corresponds to all frequencies. So this is K. This is spatial frequency here. So, and you could, and then you could do it the other way. If you spread them out, these guys get closer and closer together until you got like infinitely fine spikes on this side. So that's the Fourier transform of a comb. And then what we do is we do a convolution on this side. And that equals our answer. And so what is a convolution? The convolution, it's kind of like a correlation done at a whole bunch of offsets. That's the meaning of convolution. So like correlate this thing with this function down here, and then move one of the other ones. Like you could move this one, just move this one, and then correlate again, move this one, correlate again. And so what does that do when you just have a spike? All it does is it just makes a copy of that. It makes a copy of that brain. And so then right here there'll be another copy of the brain, etc. It'll go on forever. So that was the argument from last time for why we get a replica. So this guy's replica over here. And we could also, this is, so what's causing, what's causing this? This is from, finite spacing between samples. That's what's causing the samples. That's what's causing the replicas. Finite spacing. So this down here, finite spacing between the samples. So this is kind of a counterintuitive. We talked about the effect of finite spacing between samples on if you're sampling a time signal. So if you have a time signal and you finitely sample it, there's various problems that can arise if you don't sample it fast enough. That's kind of, for me, the intuitive entrance into this idea of sort of finite sampling. This is sort of the inverse of that. Instead of finitely sampling on the time or space side, you're finitely sampling on the spatial frequency side. But it has the same effect. And so at the end, I'll talk about the same thing, but what if this was the time side? So if this was the time side and we we finitely sample, we get replicas on the frequency side, on the temporal frequency side. And so at the end, I'll go over that example. So what does it mean to have a replica on the frequency side? Here we were looking at replicas that were occurring on sort of the time and space side. Okay, so that was what we did last time. So now let's talk about the ringing. How does the ringing actually work? Which is a different thing. So this was a finite spacing between the samples, but we're doing another thing. So that's the delta K there. So we're doing another thing, which is we're not sampling out to infinite spatial frequencies. That's a different infinity. And so what's involved there? Well, it's the sinc function again. So here's the space side again. And here's the k-space spatial frequency side. So now we start off with our brain, which just looks like a rectangle function. So here's our brain, dark, brain, and then dark again. So sorry, I'll label that. This is the brain. Brain. There we go. Okay. So we start off with the brain again, and what does that transform to? It sort of transforms to something that sort of looks like a sink. Bright spot in the middle, and sort of little ripples going away. But now we're going to do something else, which is we're going to model the finite sampling range. So the finite sampling range is basically multiplying this guy by a rectangle. So if we multiply that guy by a rectangle function, so here's a rectangle function that we're multiplying by. But now it's a big rectangle function, but it's a rectangle function. We're just cutting off, basically we're cutting off our spatial frequency sampling limit. So it's the same argument. Let me just make this guy a little smaller brain there. Okay. So if we remember, the typical sort of Fourier transform pairs, what happens if we make the rectangle bigger? It makes the sink smaller. So on this side, we're going to have a very small sink. So now it'll be, a little shrimpy sink like this. Because we have a bigger rectangle on this side. So what does it equal on this side? It equals our goal, and our goal, is a finite range of frequencies. And so what that is just our sink function like this. We can just let it go. We can forget the sampling part. You could add the sampling into this too, but we'll just leave it there. And then it just stops. It stops hard right at this point. You just cut it off. And that's the thing that actually causes this ringing behavior. But how do we represent the ringing behavior? Well, we're going to have to convolve the brain with a sink, but it's a very narrow sink. And so so now that's a little bit more of a problem. So one way of sort of thinking about this, sort of intuitive way that I suggested thinking about convolution is just thinking like a Photoshop filter. Like you apply a blurring filter. What does that do? It just kind of smears out something that's in your image, and then you get the output image, which sort of has, at each point, it's slightly smeared out, sort of mixes in the surrounding ones. You could think of it that way, but another way of thinking of it that I talked about was, what is convolution? Convolution is basically correlation at a whole bunch of different offsets. It's the same thing pretty much as cross-correlation. So cross-correlation is like take one function, take another function, and then correlate it, and then move it a little bit, one of the functions a little bit, and then correlate it, keep doing that, and then you get an output. So a correlation across both functions is one point on the output, and then you move it, and you get another point on the output. So if you think of it that way, that's a good way of thinking about what's going on. So you're correlating this sink function with the brain. And so in the flat parts of the brain, it doesn't correlate very well, because this thing is kind of a wiggly thing. Correlates a little bit because it's got the central spike is the biggest, and so this is a positive thing, and so there's some correlation because it's positive, but all these other sort of wiggles kind of cancel out. But what about when you go to the edge of the brane? So when you go to the edge of the brane, you could imagine, let's put a sink right here. So here's a sink right there at the edge of the brane, like that. Let's correlate that. You can see that there you're going to get some correlation because, you know, those vertical slopes of the sink and the brane, near a vertical slope, is going to correlate. And then if you move the sink a little bit over, it's going to negatively correlate because, you know, this guy will be going down and that guy will be going, you know, going up. And so you actually get a negative correlation. And then as you move off into the flat part, the correlation will go down again. And so what does that look like? It looks like a little sink superimposed on the edge. So if you've got the brane there, what it looks like is, when I'm exaggerating how big the effect is so you can see it, but what happens is it kind of goes like, the ripples are very small here, and then you start getting some ripples, and then there's a ripple at the edge like that, and then it goes down. So it looks like sort of like a little sink pasted on, like a half of a sink pasted onto the edge of the brane there. So and it goes down, and it goes up. You get little ripples like that, and that's what is called, you know, Gibbs ringing. Right there. And what it comes from is not sampling enough infinitely fine spatial frequencies, but it has a very irritating property. And the irritating property is that, well, what if we just went out and sampled more? Could we fix it that way? So, like, obviously if we cut off and don't sample high spatial frequencies at all, it'll be bad. But what if we just like sampled higher and higher spatial frequencies, because the problem is we didn't sample all the spatial frequencies. But sadly what happens is, if I draw it sort of a little bigger, say you've got some Gibbs ringing that looks like this, sort of drawn something like that at an edge. So that's just like an expanded version of this. What happens if we sample essentially a higher spatial frequencies? Well, irritatingly, what happens is the height of the wiggles is just as high as it was before, but they get narrower. That's all that happens. And so what happens is this height of this little sort of artifactually too bright part is fixed. And so unfortunately you can't get rid of the stripe. All you can do is just make this little stripe narrower. And so what does it look like on an image? What it looks like on an image is wherever you've got an edge on an image, so if you just go to the edge of the brane, so here's a bright thing, and there's the edge of the brane, what's going to happen is there's going to be right when you get to the edge, it's going to be even brighter. And then right when you get into the background, it'll be even darker. So it'll sort of increase the contrast of the edge artifactually in a way that's actually not there. And this was actually a problem, and the other problem with this is that it works in 3D. So say you have something like a knee cartilage. So what will happen is, right at the knee cartilage, you'll get it where you have a sharp change in the brightness of the image, because cartilage looks different than, say, the fluid that's in the joint. What will happen is you'll get a little artifactual bright stripe on the edge of the cartilage. And for a long time, radiologists looking at these assumed that that was actually a real thing. And they said you had to have this trilaminar structure in the joint to have a healthy joint, but it was actually just an image artifact because of this Gibbs ringing from not sampling out to infinite spatial frequencies. So there's various ways of fixing this. One way to fix this is just very gently smooth. So if you very gently smooth, what will happen is you'll, like say if I smooth just right across this little region like that, what's going to happen is, so if I run a smoothing filter across this, what will happen is it will sort of squash down those high frequency little spots at the cost of slightly blurring your image. So that's the Gibbs ringing. So everybody okay on that? So it's all sinks. So we just use the sink in two different ways. Here it was, you know, we've got something that looks like a sink in K-space, and we sampled it, and then it caused the replicas because of this relationship between what spikes look like when you Fourier transform them. And in this case, we've got a sink over here again, but now when we cut off our spatial frequency sampling, so this is all, you know, this is all x going in this direction and k going in this direction. When we cut off, you know, the make a finite range of frequency samples, it's the same as multiplying by a big rectangle, which is a sink, and then we just convolve that sink with our image, and then we get this little ringing thing. Okay, so is that pretty okay with that? So if you look at any image on the scanner, just basic image on the scanner, you'll see that. You'll see that little artifactual. It's kind of, in some respects, it's kind of like a good thing, because it increases the contrast of edges slightly more than they should be. And that's not, you know, a lot of times when you're doing image processing, you do that on purpose. Like you run an image processing filter that will make the edges more apparent, because, you know, the edges are where there's a change between tissue types. Obviously, if you're trying to measure something about the tissue, you know, in that case, you would want to correct for this. But this is just a problem that occurs. Okay, so now let's just talk about field of view and sort of changing field of view and what it looks like on the scanner. And unfortunately, so I'll draw four different cases, sort of like a starting case, and then we'll fiddle with the field of view with a couple different cases, and then finally come up with a slightly useful case. So we'll start off with, so now we're on field of view. So we'll start off with our, you know, original image. Not original image, so our original case. So our original case, where we sort of do things right. So we have, you know, K-space up here, so K-space on the top row, and then, you know, our image down here. So what are the basic sort of equations for the field of view? They're sort of like almost too simple. So the basic equation is the field of view, say in the x direction, could be, we have a field of view separately in the y direction. So the field of view just equals 1 over the K-space sampling interval. That's it. There's almost nothing to it. So delta kx just means how much spatial frequency do you have to increase until you get another sample. And so you could measure spatial frequency different ways. One way, intuitive way that I've talked about is number of cycles across the image. So if you have like 5 stripes across the image, that's spatial frequency 5. So what's delta k? Delta k means how much do you go until you get another sample. So delta k could be 1, in which case the next sample would be at spatial frequency 6. And so that's one equation. And then the other equation is what is the voxel size? So this is the field of view. And what does the field of view really mean? What it means is how far do you have to go until you start repeating? You know, how far do you have to go till you hit the replicas? That's really the meaning of the field of view. And so this guy was, you know, K-space samp interval. This one's the voxel size. So what's the voxel size? The voxel size is obviously just the field of view divided by the number of voxels. So this is whatever the field of view was in centimeters or meters or millimeters divided by just n. And n is just the number of voxels. It's number of voxels, but it's also number of k-space samples, right? Because if you have like 256 points in k-space, you get 256 image points. So it's it's both of those things. And so then that will, you could also write it out as just, since this guy's just 1 over k, you could just write it out as 1 over the number of voxels times the sampling interval in the x direction. So when you look at that, it's kind of, it's too simple. How could that be, it just sort of seems like it's too simple. But let's just work through simple examples to sort of show what that looks like. So our original case, we more or less do things correctly. So let's just take, so there's the center of k-space, and let's take 5 samples. So 1, 2, 3, 4, 5 samples in the x direction, and then 5 samples, 1, 2, 3, 4, 5. So when you do the Fourier transform, the discrete Fourier transform, this whole k-space picture has 11 going across because there's the center of k-space plus 5 positive and 5 negative ones. And when you work out sort of the Fourier transform, a lot of times what they do is one of these guys, either the left or the right end, belongs to the next replica. So you'll only have like 4 on one side and 5 on the other side. That's how that's how it works, which is a little disturbing. But if you got 256 voxels, not a problem. Okay, so let's just go over these simple equations here. So we have n equals 10 because we left out 1 because it belongs to the next copy over, so the maximum frequency we're going up to is 5, and the sampling interval, so delta kx equals 1. So we're doing like spatial frequency 1, 2, 3, 4, 5. And so then what's the field of view? So the field of view is just 1 over the sampling interval, so that's 1. And what's the voxel size? So the voxel size is just the field of view, which is 1 divided by the number of voxels, and so the voxel size is 0.1 in whatever units we're using. So that's our starting condition. So if we Fourier transform that guy, so this is the Fourier transform direction, ft minus 1 direction, then we get our brane. So here's our brane, and there's another brane. There's another replica over here, and another one over here, etc. Another one up here. So, and what is the voxel size? Here's our standard voxel size. I'm drawing it too big, but say our voxel size is something like that. So now let's start messing around with our data. And so one of the things we could do is sample out to a higher spatial frequency. So there's our original case. Now sample to higher kx, higher spatial frequency. So what does that look like? So here's our k-space. Here's our original k-space. Say we just sample out to twice as high spatial frequency. So like go out another distance like that. but keep the same number of sampling points. And so what does that look like? So in the y direction, it's exactly the same. So 1, 2, 3, 4, 5. But now what we're going to do is do the same number of samples we did before. This is the original one here. Same number of samples we did before, but just spread them out like 1, 2, 3, 4, 5, like that. And so what does that do? Well, first of all, like let's just run our equations. And so if you run the equations, so the sample number is the same, equals 10. Maximum kx is now 10. And so the delta kx equals 2, because we're only sampling every 2 spatial frequencies. And then the field of view in the x direction is the field of view is 1 over that number, and so the field of view is now smaller because the sampling interval was bigger. So it's just it was 1 over 2, so we got 0.5, and so then the voxel size, we're dividing by the same number of n, same number of voxels, so the voxel size is going to be smaller, half as big, 0.05. So what happens, so counterintuitively, what happens when we did that? So here's our inverse Fourier transform to make our image. So one thing that's confusing is that the scanner has a square display window. So the scanner a lot of times will just show you something, and it won't necessarily show you the actual field of view. It will sort of show you just a square. And so what's going to happen here? Well, our field of view has gotten smaller. It's gotten half as big. So our field of view is only like this big. So here's the actual field of view, like that. And so now the brain is still in there. Brain hasn't changed size. So the brain is still in there. It looks like this. And so what happens? Well, the replicas are going to come in. The replicas are going to come in because we're not sampling k-space as finely as we did before. Because remember the previous board, as you space out the sampling, the replicas come in. If you make the sampling really fast, the replicas go away. And so there's going to be another brain here. So here's another brain like that coming in. And there'll be another frontal lobe poking in on this side like that. And you'll actually see a little bit more of it than you would normally because the scanner is just sort of showing you a square. So it'll actually replicate some of the image, which makes it even more confusing. And so you get wraparound, but what is wraparound? Wraparound is like the frontal lobe, in this case, it's the frontal lobe over here intruding in to the occipital lobe, and then it's the occipital lobe of this replica intruding into the frontal lobe. So the image will be twice as bright where those things are on top of each other. So that's another problem, like not only will it be overlapping, but it'll be twice as bright. So what happens to the voxels? So the voxels have gotten thinner in this axis, but they're the same thickness they were in the other axis. So you've actually you're made a higher resolution image, which will be shown using the same number of pixels in the x and y direction on the scanner. The scanner will show you sort of the actual width of the voxels properly. It won't show you the width of the field of view properly because it will still be. So this is the scanner display. So so that's kind of useless. So what if we just sampled more finely? So here's another. We'll finally work ourselves up to something that's actually useful. So now if we sample more finely, but sample the same range of spatial frequencies as we did before. So here in the x direction, 1, 2, 3, 4, 5 as before, but now we got 1, 2, 5, 6, 7, 8, 9, 10. So we'll sample more finely in the x direction. And what does that look like? Well, now that's going to be the number of samples now equals 20, and but we're still going up to just kx equals 5. And what is the sampling interval? Sampling interval is just equal to 0.5 now. And the field of view in the x direction should just be 2 now, because we're dividing 1 divided by 0.5. Smaller number in the denominator, we get a bigger number. So we double the size of the field of view, and then the voxel size, this double-sized field of view divided by a larger number of points is exactly the same. So it's 0.1 still. So what do? We kind of had almost no effect on the image here. So if you look at the image, you're just going to get a brain, and it will still be on a square, but what will have happened is that the actual field of view will have gotten bigger by that much. So here's the actual field of view. It looks like that. So this is actual field of view. And so what happens is you just move this replica away. So there's the next replica. And if you look at the voxel size, it's exactly the same as it was before. Didn't change. So everything looks exactly the same. So you might think, wow, that wasn't a help. So let's just annotate these. So here's our basic image. And then, so x pix, the x voxel, half width. So we increased our resolution here. But we also decreased our field of view, which means the replicas came in. So we have this sort of, wraparound. Looks like wraparound. So it's confusing. It's partly confusing because it's not actually, like, look at the frontal lobe. It's not actually the frontal lobe sort of wrapping on itself. It's actually the occipital lobe, the back of the brain, coming in and wrapping around the front. So it's a little confusing because it almost might look like all you did was you just folded the frontal lobe around. You didn't do that. You actually sort of got another copy of the back of the brain pasted onto the front of the brain. Okay, so what happens in this case? So still square pix. So our pixels are just the same as they were before. The field of view is 2 times bigger. And what is this confusingly called on the scanner? This just always cracks me up. It's called, so the problem is I'm sort of describing it sort of from the basic simple mathematical description. When you go to the scanner, it's got all these different names for this, which don't necessarily directly relate. And so this is called phase oversampling. So nobody in their right mind would be able to figure out what's actually going on from that. So phase oversampling. So what does that mean? So it means, like, if we look at the original correctly sampled one back here, what have we done? We've sampled too much. So there's something you can type into the scanner, phase oversampling, if you want to do this, because sometimes you might want to do this because you might want to actually, maybe you've got a really long brain and the nose is coming into the occipital lobe. So then you would want to do phase oversampling. What are you actually doing? You're just actually collecting more finely sampled k-space. And how do you do these various things? Like, how do you sample out to a higher spatial frequency? It's very simple. All you do is just turn the gradients up. So if you just collect everything the same, exactly the same data in time, but you just turn the gradient up, then what will happen is it will wrap up more spin phase stripes in the same amount of time. And then if you collect the data at the same spacing in time, you'll just end up with higher stripe count. So that's how you would sort of like sample up to a higher spatial frequency. How would you do this thing here? Just turn the gradient down. So if you turn the gradient down in this case and sample at the same rate, then you'll end up getting finer samples in k-space. Those intuitions are relevant because that affects the amount of time. Because like how much time are you using to record the data? It's going to change the overall length of the scan, and we're always like trying to make the scan, as short as possible. But there is one good thing that happens with this: you get better signal to noise. And think about this; it's kind of counterintuitive. All you did was scan more air. So this is something that's very counterintuitive. So we made our image better. So we made our image better here. We didn't change the voxel size at all. All we did was just expanded our field of view to include more air. And what did it do? It made our signal to noise better. And why is that? Well, we collected more data. We collected 10 points here instead of 5 on the positive side of k-space. And so that's also completely counterintuitive. Like if you're on the scanner, you say, like, I don't want to waste, scanning any air. Like, why am I scanning air? I want to make the field of view as small as possible. But if you make the field of view bigger, you'll actually get a better signal to noise at the cost of a little bit longer to record the data. Obviously, you're recording more data. So, so if everything else held constant, you actually get better signal to noise. So finally, let's do something that's vaguely, slightly. I remember when I first stopped here back, a couple of years ago, and then somebody said, like, well, that's completely useless. Can't we actually do something that's vaguely useful? So here's something that's vaguely useful. So now let's just record out to a higher spatial frequency, but more data points, but spread out at the same delta k interval. So here's our original k-space, and so now let's go out an extra distance like that, and we record the same 1, 2, 3, 4, 5 this way, but now we're going to do 1, 2, 3, 4, 5, 1 like that. So now we have the same. So now we've got 20 samples instead of 10, and the kx now is going out to 10, and our sampling interval is 1 now, and so the field of view gets bigger because now it's 1 divided by, did I do that right? Oh, no, sorry. No, field of view is the same, right? Field of view is the same because it just depends on the spatial frequency sampling interval. And then the voxel size, however, does reduce because we've got more samples. So now we should be 0.05 again. So that sort of did something useful for us. And so what does that look like on the scanner? It just looks square again. And the brain's the same size. And all we did was we just decreased the x voxel. So we made the x voxels finer, but we left the y voxels the same size. So this is, x pix half width. And the field of view is the same. And what about the signal to noise? Signal to noise will be slightly worse. And so why is that? Well, we made the volume of the pixels smaller. So when the volume of the pixel, remember the signal to noise equation, the most important part of it was the volume of the pixels. So we reduce the volume of the pixels, that's going to reduce our signal to noise, but we're collecting more data. That's going to help our signal to noise, but it's under the square root. The number of data points is under the square root, so we get slightly worse signal to noise in this case, partly compensated by the fact that we collected more data, which took more time. But we made our voxel size smaller. So that's something that's kind of useful. It doesn't change the field of view. It just sort of increases the resolution. So the problem on the scanner is, how should this really be set up? It really should be set up where you should have a table that has field of view, because these things obviously affect each other. So this is, and back at UCSD, before we got our real scanner, we got a scanner that didn't really have an intercom initially, because it was from a company that sort of was involved in scanning chemicals. What do you need? What do you need to talk to the sample for? So what you really want is just a table like this, for X, Y, and Z, because these are all, there's a table of 9 things. So if you set the field, so if you set any 2 of these, if you just look at those equations, if you set any 2 of these, it's going to affect the other one. So what is the matrix? The matrix is, n. How many data points are you collecting? And you can set that on the scanner. Usually it kind of yokes the X and the Y matrix to each other, even though you don't have to. And then if you're doing a 3D scan, you can set sort of the matrix. It's relevant to set a matrix size in the 3D scan. If you're doing a 2D scan, it's different because you have slices. And so a lot of times, because people started off with 2D scans, they don't kind of properly represent how the 3D scan is actually working on the scanner interface, because they sort of still have slices, and there's really no slices in a 3D scan. But this would make it a lot easier, because then you would just have, if you change any of these, it's going to change the other 2. So you only have to set 2 of them. You set your field of view and how many voxels, what the voxel width is. So voxel width. And then that will tell you what matrix you need. Or you could turn the matrix up for a given field of view, and that will affect your voxel size. But these are some things that you do on the scanner. You're sitting in the scanner, you say, I want higher resolution, and so what should I set my matrix size to get a particular voxel size? And they're just these dead simple equations. Just field of view is 1 divided by your sampling interval, and the field of view divided by the number of samples is the voxel size. So you'll do that division a lot on the scanner. Okay, so before we go out with aliasing, any questions about this? So these are practical things you actually do when you're on the scanner trying to decide how to scan the elephant brain with small enough voxels. So any questions? All okay? Field of view. It's a strange replica business, but that's just the way it is. All sort of clear. When I first saw this equation, I said, that's it? Is that it? The field of view, there's not enough numbers in it. It's only 1 number. 1 divided by the sampling interval. It doesn't seem like that's enough, but it's very, the math is actually very simple in a way. Okay, so last thing, let's sort of go back to replicas, which are kind of like the way that I first had this idea of wraparound in the frequency domain. And this is going along with this discussion of like the Nyquist sampling interval. So this was, if we think about, so the whole time here we've been talking about sampling interval in frequency space, k space. So what's the distance to our next sample in frequency space? Or just in concrete terms, how many, what's the next spacing of stripes that we're collecting a data at? So the alternate way of thinking of it is, what if we're sampling in time, or it's like sampling in space or time? And what if we don't sample often enough in space or time? What happens to frequency space? So what happens to frequency space is you get wraparound. So it's the opposite of what we were talking about. We were talking about we don't sample often enough in space or frequency space, and we get wraparound in the image, non-frequency space. But the inverse is true too, converse is true too. And so let's make a illustration of this. So let's start off with a couple. Let's do here, 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 here. I need some marks so I can make a good sine wave. So let's start off with like sampling an audio signal. So we're just going to take some samples in time of this audio signal. And the audio signal has a couple frequencies in it. So here's one frequency in it. So this guy is like this. So I got drawing good quality sine waves. Kind of went off toward the end. Okay, so now what happens if we don't sample this often enough? So say so how fast would we have to sample it to sort of capture this correctly? We would have to sample it at least twice as high as this frequency so that we could sort of have a chance of catching the ups and downs correctly. So say we're sampling slower than twice the frequency. So let's sample, say, let's sample at this. So this is our delta t. So that's our sampling rate, also known as the bandwidth, 1 over the bandwidth. So that's our sampling rate. So we take a sample here. So there's a sample there, and then here's another sample here, and then here's another sample here. Let's get this there, 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 another sample here, another sample here. So what happens? Well, we get something that looks like a low frequency signal. So what is that? That's actually a replica. It's from a replica in the frequency domain. So now let's see what happens if we have a higher frequency. Let's just make a frequency that's twice. So here's that higher frequency. And so now what happens when we sample that guy at our same sampling interval? So here's, I have to draw the sampling interval in there. This one was right on the money. So if we sample this guy, what's going to happen? So now what's going to happen is we'll get another aliased signal. So what is this? This thing is called an aliased signal. And how do we fix that? We could fix it just by filtering out any of the frequencies that were too high, or we could fix it by just sampling faster. Either one will fix the problem. So now what's going to happen, if I've drawn this well enough, we're hopefully going to get a higher frequency. Now we've so now what happens is we basically get a higher frequency. You can see the spacing between these peaks in this alias signal. So this is a higher frequency aliased signal. And so what's going on here? Well, we're getting a replica in frequency space. So if we draw out our frequency space, say we've got a frequency spectrum that looks something like this. We got some low frequencies and we got some high frequencies. That's what's actually in the signal. So this guy is the actual spectrum. So just make sure that we know where we are. So here this is frequency, and then this guy is time. Okay, so we got some actual high frequencies there, but let's just say that we only sampled out to that frequency. We didn't sample to a high enough frequency. And so what is that going to do? It's going to cause a copy of the spectrum. So basically, it's going to cause another copy of the spectrum to be superimposed on it. So it's going to be another copy right here. And that guy's a replica. So this guy is a frequency domain replica. And we worked it out. You can see we just worked it out geometrically here. So what happened? Well, here was a higher frequency. So there was a higher frequency here, say this guy. And what happened to that one? Well, it came in and appeared as a lower frequency. We'll just put it on its replica there. And then what happens to an even higher frequency? So an even higher frequency is going to appear as a somewhat higher frequency, but wrapped around into the, this is low and high in this direction. And then what's yet an even higher frequency is going to come and appear here. So what is this useful for? Well, if you have something like, say you're recording some fMRI data, and you record a data point every 2 seconds, which is not an uncommon rate of recording. So every 2 seconds you're recording a data point. But at the same time you're breathing, you're breathing every second or two, and your heartbeat is beating, if you're nervous, it's beating like 2 times a second. But if you're sort of a scanner, an old hand at the scanner, then you're falling asleep and your heart rate is only like 1 beat a second. But we're only recording data points every 2 seconds. And so what is that going to do? Every time your heart beats, it causes the oxygenation to increase. And so you end up with a bigger signal every time your heart beats. It's pretty big variation in the signal because it's pumping oxygenated blood and you're measuring something, the effect of oxygenated blood. And so what's going to happen is that signal, which is off the edge, you're not recording fast enough, is going to come and appear as a frequency signal in your time series it's at a very low frequency. So the heart rate 1 per second was the highest frequency that you're recording. You're recording 1 every 2 seconds. That's the highest frequency that you're recording. Your heart rate is faster, higher frequency than that. That's going to appear in your times sequence signal as a low frequency signal. And what's a low frequency signal? Well, that might be your block design. You know, maybe you were having somebody look at faces and then upside down faces. And so what can happen is this signal, this alias signal like this, that is actually coming from, the heartbeat. It's going to wrap around and appear at a low frequency in your data. And so that potentially could be a problem. So there's an example of like a real life case of where our sampling rate was not fast enough. Unfortunately, there's no easy way to fix this because you can't easily filter that signal out because you're recording it with the fMRI. You know, there's no way of filtering out the heartbeat. You could try to record the heartbeat and maybe try to patch it up afterwards, but this is a chronic problem with collecting fMRI data. It's hard to collect it fast enough. Now, if you could just collect an image every half a second, then that would be fast enough so you could actually see that signal in your time course and filter it out. But the problem is once you've got this aliasing, it's hard to deal with, you know, after the fact. Okay, so that was just sort of going back to our very, you know, sort of replicas. So this is aliasing. This is basically replicas in the frequency domain, as opposed to, you know, replicas in the non-frequency domain. Okay, so all good on the replicas, and it's very foreign. Like, you know, I kind of understood this. I could see this picture of, like, you know, you accidentally get a lower frequency signal out because you're not hitting the peaks, or you're just sort of hitting the offset. You're hitting this high frequency signal at a different point in its phase. And then you can see that if you make an even higher frequency signal, it's going to do the same thing but make a higher frequency aliased signal. I could sort of understand that, but it's very strange in sort of this spatial frequency domain, and just thinking about, you know, undersampling in the spatial frequency domain. Okay, so any questions out there? All good. Last of the Fourier. So last of the engineering greatest hits. And so now we'll just talk about actual pulse sequences for the next couple weeks, ones that you might actually use. Okay.